This is Calculus 12, Chapter 4.3. This time we're going to be learning how to use the first derivative and the second derivative to graph a function. This is Theorem 4, and at a critical point C, if the derivative is greater than 0 for x is less than c, and the derivative is less than 0 for x greater than c, then f has a local max at c. And a critical point means the derivative at c is going to equal 0 or does not exist. Now let's put into more descriptive words. If the derivative is positive and we're to the left of c, and the derivative is negative and we are to the right of c, then it has a local max. Okay, and number 2 is similar. It's the opposite. If the derivative is less than 0 to the left, and the derivative is positive to the right, then f has a local minimum at c. Number 3 is different. If the derivative does not change sign at c, then f has no local extremum at c. We'll call this number 4, and we'll call this number 5. At the left-hand point A, if the derivative is negative for x greater than a, so this is to the right, then f has a local max at a. Now we're going to use the same wording. However, we're going to change this. If the derivative is greater than 0 to the right of a, then f has a local min at a. So if you want to picture this, if the derivative is less than 0 at endpoint a, okay, so that's clearly a maximum. And here, if the derivative is greater than 0 at a to the right, this is a minimum. Okay, and number 5 just rounds it off for us at the right endpoint. So to the left of b, f has a local max if the derivative is greater than 0. Okay, so we can look at this. The derivative is greater than 0 at b, to the left. So that's a maximum. And we'll do the opposite. If the derivative is less than 0, then we have a max. So at b, the derivative is less than 0. And this is a minimum. In Pre-Calc 11, you learned about concavity. Here we're going to do a more general definition of concavity. The graph of a differentiable function y equals f of x is a, concave up on an open interval I, if the derivative is increasing on I. So what does this look like? The derivative is increasing on I. So we have negative derivative, and it's increasing. So we're not talking about whether the derivative is positive or negative, it's just increasing. So this is a large negative number, say negative 4, then negative 3, then negative 2, negative 1, 0, 1, 2, 3, 4. So the derivative is increasing. And then we have the opposite case. It's concave down on an open interval I if the derivative is decreasing on I. Concavity test. Okay, so the graph of a twice differentiable function y equals f of x is concave up on any interval where the second derivative is greater than 0. So this means positive. And here it means negative. So I think we can see that this definition may be a little bit easier to work with than that definition. Point of inflection is a point on a graph where the second derivative changes sign. So going from positive to negative or negative to positive. And just because the second derivative is 0 or does not exist does not necessarily mean that it's a point of inflection. Okay, so let's look at this. At this point, roughly, this is going from concave down to concave up. So this is an inflection point. Again, here we have an inflection point going from concave up to concave down. Here, the second derivative does not exist, but we are going from concave down to concave up. So let's put this down, concave up, concave down, concave up. Here, the second derivative does not exist, but we don't have a point of inflection because we're going from concave up to concave up. And we have concave up and concave down. The ones where I filled in purple, these are points of inflection. Second derivative is less than 0. Second derivative is greater than 0. Second derivative is less than 0. Second derivative greater than 0. Second derivative is greater than 0. Second derivative is less than 0. Okay, theorem 5, second derivative test for local extrema. So if the first derivative is 0 and the second derivative is less than 0, then it has a max at the critical point. Similarly, if the first derivative is 0 at c, second derivative is greater than 0 at c, then f has a local min at the critical point. So let's look at these and try to come up with reasons. Okay, the tangent here is 0. So this is a max because the second derivative here is less than 0. So we're using theorem 5, part 1. Here, it's an endpoint. So we're using theorem 4. So that's at the beginning of page 1. And it's a min. So that's number 4. This is the left endpoint. And we might as well do this one. This is theorem 4, and it's a right endpoint. And the derivative is less than 0, so this is a min point. It's less than 0 to the left. Okay, here we have a min, and the second derivative is greater than 0. Here, we're not using the second derivative test because the first derivative doesn't exist and the second derivative does not exist. So that means we need to use theorem 4. This is a max. And we're using theorem 4. And we're using part 1. Here we have a min. Second derivative is greater than 0. So both of these are theorem 5. And we're looking at part 2. This is a max. And we're using theorem 4, part 1. Okay, the derivative does not exist. The first derivative is positive on the left. It's negative on the right. Here we have f prime and f double prime equals 0. So there's no extrema. And if you want to give it a reason, this is Theorem 4, Part 3. The derivative does not change sign, so it's negative on the left, negative on the right. Okay, let's look at an example here. And we're missing the y-axis. Okay, I've already drawn the graph for you, but that's not the only solution. We start off with some key information. The function is continuous on the domain -2 to 4, including the endpoints. At -2, we're starting off at 5. So this is 1, 2, 3, 4, 5. So that's a fixed point. We can't do anything else with it. And at 4, the value is 1. So 4, 1. Now we have to make sure that the first and second derivative have the following properties. So we want the first derivative to be positive and the second derivative to be positive. So this is all positive and it's concave up. And at 0, we want the first derivative and the second derivative to not exist. That means we have a cusp. It can't be a corner because a corner means that this would be a line and this would be a line, and the second derivative would not be positive over here. It would be 0, and 0 is not positive or negative. Okay, so here from 0 to 2, we have negative slopes and we have concave up. So these slopes are all negative and concave up. And we want the first derivative and the second derivative to be 0. So that must mean this is an inflection point. And finally, we have negative slopes and concave down. So these are all negative slopes and it's concave down. So if we want to label this concave up, and the derivative is greater than 0, first derivative does not exist, second derivative does not exist. This is -2, 5. This is 4, 1. This is concave up, and the first derivative is less than 0. First derivative is less than 0, and it's concave down. And we want to find all absolute extrema. So this is absolute max. This is absolute min. And if we want to label this one, this is also a local min. And that's all we have to do for that one. So, like I said, this is not the only solution. You can also sketch the graph like this, come down, have your inflection point, and end up at that spot. Okay, let's look at a polynomial example. I filled this out for you because you should know how to do this. Taking the first derivative, we're just using the power rule on every term. Second derivative, power rule on every term. That's a mistake. We'll say x equals -1 works, and we'll plug it in. So -1, this is +3, this is +1, and -3. It all cancels out, so it's 0, so that is a factor. We're taking this from Pre-Calc 12, Chapter 1, using the factor property. Now we're going to use synthetic division. We divide it out. We get a remainder of 0, so that confirms that it works. We're left with x squared plus 2x minus 3. We can factor this. So we have these 3 factors. Okay, now let's look at the second derivative. We need the second derivative equal to 0. This is not factorable, so we have to use the quadratic formula. And for those who've forgotten the quadratic formula, we have x equals minus b plus or minus square root b squared minus 4ac, and the whole thing over 2a. And a lot of people make the mistake of not putting the minus b over 2a. So substitute the values. We get negative 6 over 6, so I simplified this to negative 1. And since we're sketching, it's good to just round this off. So this is approximately negative 1 plus or minus 7 over 6. And these are our inflection points. So this is approximately 1 over 6 and negative 13 over 6. Because the square root of 48 is pretty close to the square root of 49. 49 we can use an exact value. Okay, time to do some calculations. Generally looking at the function, we have a positive a on an even function. So y is generally concave up because a is greater than 0, so there's no global max or absolute max. So now we need to evaluate these. So we'll start off with y of negative 3, and then we just substitute negative 3 into the equation. We get 1/4 negative 3 to the power of 4 plus negative 3 cubed minus negative 3 squared over 2 minus 3 times negative 3 plus 2. And you can do the arithmetic there, and this will give us negative 1/4. Y of negative 1 equals 1/4 minus 1 minus 1/2 plus 3 plus 2, and this gives us 3 3/4. Y of 1 equals 1/4 plus 1 minus 1/2 minus 3 plus 2, and that gives us negative 1/4. We can also plug in one more point. Actually, we should plug in one more point. We do y at 0 to calculate the y-intercept, and that's just 2. So now we can draw some conclusions. This is smaller than this, so this is, and this is equal to this. So this is an absolute min. This is an absolute min. And we said there was no global max, so this is a local max. So let's graph this. We'll start off at negative 3, and it's negative 1/4. At negative 1, we have 3 3/4. At 0, we have 2. And at 1, we have negative 1/4. Now we go ahead and sketch. We know this is a maximum, so we'll come down, make it nice and smooth, and go up. This is coming down and going up. Okay, just to the left of negative 2, because we have negative 13 over 6. So just to the left of it is going to be an inflection point. And just to the right of the y-axis, we have another inflection point. Because 1, 6 is just to the right of the y-axis. Okay, we can draw our boundaries. This is concave up. This is concave down, concave up. And we can label this as absolute min and absolute min. And we can also do our intervals of increasing and decreasing. So this is decreasing because the derivative is less than 0. And here it's increasing because the derivative is greater than 0. And on this interval, it's decreasing because the derivative is less than 0. And here we have increasing again, and the first derivative is greater than 0. And we'll label some more points. The derivative here is equal to 0. The derivative here is equal to 0. Derivative here is equal to 0. And we'll label our y-intercept. Okay, so the second derivative test may fail when the second derivative equals 0 or does not exist. So for determining extrema, fall back on using the first derivative test, which is theorem 4. And here's an example where it fails. If we have x to the power of 4, the first derivative is 4x cubed, the second derivative is 12x squared. Both derivatives are 0, so we have to check the derivative on one side, check the first derivative on the other side. This is negative on the left, positive on the right, so f of 0 is a minimum. And that completes this lesson.